Hello everybody, this is going to be a quick review of the concept of equilibrium that you learned about in Honors Chem. First, equilibrium is only going to occur when we have what is called a reversible reaction. A reversible reaction is one in which you can form the products, or you can go backwards and you can take the products and turn them back into the reactants. Not all reactions can do this. They are not all reversible. So this will only apply to reversible reactions. Chemical equilibrium is what we call it when the reaction finally reaches a point in which the forward reaction speed is the same as the reverse. So the concentration of the products and reactants don't change. Every time you make a product, you're going to break one apart and turn it back into a reactant. So even though the reactions are still occurring forward and backwards, the concentrations won't change because they're happening at the same speed. When we have an equilibrium equation, a reversible reaction, we use a double-headed arrow. You can see people draw these in a variety of ways, but the idea here is we're trying to show people that you can go forward or you can go backwards. If you remember this graph from Kinetics, it was really important that we took the instantaneous rate when the reaction first began. Remember we did those problems where you had a bunch of rows of data that showed you the concentrations changing and then you had the instantaneous rates? Well, the reason it was important to measure at the very beginning of the reaction was because as the reaction proceeds, we finally will reach a point at which it kind of plateaus. The concentrations won't really change anymore. So if we measured our rates here, right, that would not at all be representative of the kinetics that we were trying to measure. This part where you get to these flat plateaus are where equilibrium has happened. Now, we are not stopping the reaction. The reaction's still going. We're still making products, we're still breaking them apart into reactants, but because they're happening at the same speed, if we were to graph our concentration change, you'd see there's no change eventually. We call it dynamic equilibrium because it's not that the reaction is stopped. The dynamic is trying to tell people that there's still stuff happening. So if you got a graph like this, you should be able to indicate on it where the equilibrium point has been reached, and that's when the concentrations stop changing. It is really important to understand that the concentrations are not equal, but the speed of the reaction forward and backwards is equal. So if you look at this graph, we have way more hydrogen iodide up here than we do have hydrogen or our iodine gas, right? One of the most common mistakes is for people to say the concentrations are equal, and that is not true. You can literally see on this graph that it is not the same concentration. These lines are not at the same place. We have way more of this one than we do of these. But look at the slope here. The speed, the rate is the same. So equilibrium is connected to kinetics a little bit, isn't it? Right? We're talking about the speed of reactions. They like to sometimes throw problems at you where you have to take equilibrium and connect it to kinetics or even to thermodynamics. If you remember from thermodynamics, we learned a little bit about how we can use our delta G value to identify whether or not a reaction is at equilibrium. Remember, this is not the same as delta G naught. You have to be a little bit careful. This is just delta G. Remember, if your delta G was negative, that was an indication that you were at this part of the graph and you were going downwards. That's why it was a negative, right? Negative slope here on delta G. We were having a lowering of our energy, which meant the forward reaction was being favored. But if you were on this side, if you had a positive delta G, that would mean that you would want to be going in the reverse direction. The reverse reaction would be favored. But if you were at this special point way at the bottom, where delta G is 0, That means you are at equilibrium. So at this point, the forward and backward reaction, neither is favored. One is not better than the other. You're not going to get any benefit from going one way or the other, so they're just going back and forth and back and forth and back and forth down here at this point. So you can see here, they may try to bring in thermodynamics to your equilibrium problems. And just one more time, I really want to emphasize that it is the rates that are equal, not the concentrations. You will hear me say that 500 times during the chapter. That would be one of those thou shalt not forget things, right? We will sometimes use the phrase product favored, which tells people that when you've reached equilibrium, you're going to have a lot of products and not very many reactants. So the reaction is favored towards the product side. Or you could have something that is reactant favored, meaning when you're finished, you're going to have a lot of reactant left over. It was not favorable to make very many products. Lastly, there's a really silly cartoon video that I'd like to show you. Some of you may have seen this in Honors Chem. Some of you may not, depending on who your teacher is. But I do think it's good to watch again, even if you have seen it. It's a really silly way to try to remember the concept of equilibrium.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. We're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
So, while that is a little bit of a silly analogy, armless people and, people with arms as noses, I do think it is helpful because I think they do a great job showing you that if you zoomed in, you would still see a lot of changes happening. But because we are looking from the macroscopic point of view, we don't see the concentrations change because they're changing forward and backwards at exactly the same rate. Okay. Well, I hope that was a helpful review of the concept of equilibrium. We'll get into the math more in later lessons. All right, everybody, that was it. I hope that was helpful. Bye.